Everyone, so it's John. We're going to work on week 8, the acids and bases. So let's go ahead and get into this. So number 1, it says, according to Arrhenius theory, a neutralization reaction occurs with the combination of hydrogen ions and hydroxide ions to form water. This is true. The Arrhenius definition requires that you have an H plus and an OH minus, and they combine together to form water. The Bronsted-Lowry definition for number 2 suggests that bases are defined as proton acceptors, so that is correct. So in the Bronsted-Lowry, the only thing that's important is the H plus, and who gives the H plus, or which molecule gives the H plus, and then who receives it. So the base accepts the proton, the acid, or the H plus, and the acid gives the proton. And then we'll see Lewis in a second. So Arrhenius is not really used that much. Really, you're going to be looking at mostly Bronsted-Lowry and Lewis. Choose the Bronsted-Lowry acids and bases in the following equation. All right, so the first thing you want to do is look at your reaction. I don't know why I keep saying equation, but look at the reaction. You look at the reaction, and I'm going to pick one molecule. So I'm picking HSO4, and the molecule that's it's most similar to on the other side of the reaction is SO4 minus, right? So if I look at the difference between these two, between HSO4 and SO4 minus, I can see that it's missing an H. So since this SO4 minus is losing an H, this is going to be the acid of the reaction. And then this is going to be the conjugate base of the acid. Right, you can go kind of back and forth if you're looking at it the other way. SO4 is a base, and then the conjugate acid is HSO4. Then we have this acetate ion. Between these two, you can see that it gains an H. And because it gains an H, that means that it's a base here. You have a conjugate acid in that other part. So the acid, again, gives the H in this case for Bronsted-Lowry. So you can just check if it loses an H or if it gains an H, right? And then determine it that way. So we can see here that the acids are HSO4 and HC2H3O2. So then the answer is going to be, looks like B. All right. So looking at number 4, it says, which of the following are Lewis bases? So Lewis base, the definition of a Lewis base is it donates a pair of electrons. So this is most commonly used in organic chemistry. It's used quite a lot in organic chemistry because you see electrons move around a lot. So we often talk in terms of Lewis bases and Lewis acids. Lewis acid is something that accepts a pair of electrons. So yeah, this is a Lewis base definition. Now, how do you know if something's a Lewis base? Well, you haven't learned the Lewis structures yet. That's in 2B. So if you're looking at these, one easy-ish way to do it is look at the charge. If it has a negative charge, it usually has an excess of electrons. Currently in the case where it doesn't, but should have an excess of electrons if it has a negative charge. And then it's going to be able to act as a Lewis base because it has excess electrons, it can give them away. Now, if it's neutral, that's different. So we have 1, 3, 4, and 5 are all neutral, right? Okay, so how do you know now? Well, boron is one of the exceptions that you should know. So boron only likes to form 3 bonds, and it needs like 6 for a full octet. So boron doesn't have any lone pairs on the central atom. That's one that you'll just want to remember. So boron has 3 bonds. It doesn't have any lone pairs on the central atom, and it can't act as a Lewis base. Now, for other things, what you can do, for things on the right side, specifically of the periodic table in the non-metal section, if you start on the noble gases column, so the 18th column, as you move down to the left in terms of columns, you can figure out how many bonds those atoms typically want to be neutral. So going one period down, sorry, one group down from the noble gases, one over is the halogens. Halogens typically want one bond. Now, you need 8 electrons for an octet. So what happens is the other 3 pairs of electrons, because electrons are always paired up, right? The other 3 pairs of electrons come in terms of lone pairs. So if halogens want one bond, they're going to have 3 lone pairs, and they can donate a lone pair of electrons, right? Because they have electrons to donate. They're not taken up in a bond. If you move one other group down, you get to like where oxygen is. Oxygen typically wants 2 bonds, which also means it typically has 2 lone pairs. So oxygen typically can act as a Lewis base. Nitrogen is in the next group. Nitrogen typically wants 3 bonds, and it typically has 1 lone pair, right, when it's neutral. And so oxygen from the H2O and nitrogen from the NH3 can both act as a Lewis base because they have a lone pair. And then the answer is going to be 2, 3, and 4 for A. Number 5, the aluminum won't, you won't have a lone pair on that central aluminum. All right. So going down to number 5, it says identify the Lewis acid in this reaction. So as we kind of just said, this one has the excess of electrons because it has a minus. So F minus is the Lewis base. And then BF3 is the Lewis acid. That's it. So boron can't donate. Boron doesn't have the lone pair on the central atom. The F has excess. So here we go. Number 6, it says complete the following equation. HCl plus NH3 is in equilibrium with what? List the conjugate acid and base pairs. Well, 2 ways I guess you could think about this if you're not thinking in terms of strong acids. You could, I guess, think in theory that the NH3 could give a hydrogen to the HCl, and you would get like H2Cl plus. It's not going to work because HCl is a strong acid, so it's going to give its hydrogen away. So there's really no cases where you're going to see 2 strong acids together, and then you'll have to guess which one is stronger. Typically, you're going to see something like a strong acid with a weak base, which we do here. There's only one case that I can think of, sulfuric acid and nitric acid. You don't have to worry about that, but you may see it when you take organic chemistry for nitrating benzenes. So we have NH4 plus because the Cl is going to give away the H, and Cl minus. Also note the charges, right? The total charge on the right is 0. You have a plus and a minus. Total charge on the left is 0. That should always be true. You have to conserve your charges. Then it says list the conjugate acid and base pairs. Put the base first in each pair. So we have NH3 and NH4 plus, right, where it gains a hydrogen. When you gain a hydrogen, it goes up in charge because it's an H plus. And then you have Cl minus, they want the base first, and HCl. So these are the bases, and then they're conjugate acids. Number 7 is in the following reaction, we have HS minus plus H2O liquid. Gives us these 2 things again. All you have to do is really look at a molecule, see whether or not it's gaining or losing an H. In this case, HS is losing an H, right? The sulfur is losing the H. So this is the acid, this is its conjugate base, and this is the base, and this is the conjugate acid. So B is correct. And that's the only one that's correct. Number 8, it says determine the value of Kc for the reaction below at 25 degrees Celsius. So we're going to do that stuff where we multiply Ks and stuff like that. So note how both of the hydrogens have to come from H3O plus because it goes from H3O plus to OH minus. Or it goes from H3O plus to H2O and H plus to H2O and H plus and OH minus. So what you can do is this, right? You can say, well, for certain products, let's see, we have, sorry, certain products and reactants. So for NH3, so we have the K, actually, let's not write out all these reactions first. So we have NH3 plus H plus is in equilibrium with NH4 plus. We have F minus plus H plus is in equilibrium with HF. We have H3O plus oh, nothing, yields H2O plus H plus. Then we have H2O turns into OH minus plus H plus. Now, if you add all of these, you will notice that nothing really cancels out except the hydrogens. Then you get the same equation that you do above, that we have above. So what we're going to do is we're going to add all of these. It's the same. If we add all of these, we get the same reaction. So we have to multiply their Ks. So we're going to use K rules. When adding reactions. So you have to have these values pretty much. Now, I think on your sheet, you're usually given the Kas. So of each of these, right? So if you're given the Ka in this form, then if you reverse the reaction, so you're going to have to take 1 over the Ka, right? You're going to take the reciprocal of the equilibrium constant, just as we did before with all those other equilibrium reactions. Ka is just another equilibrium constant. It's like Kc. So if I write this out, let's say it has just some Ka. Then if you reverse it, is 1 over Ka. Right? Just from the rules of reversing stuff. So let me pull up the sheet because I don't have these off the top of my head. We have all these values. So I went ahead and plugged them in. Just remember for the top two, you're usually given the Ka, and then we just reverse the reaction. So Ka is the dissociation reaction of the acid, or it's the equilibrium constant for the dissociation reaction of the acid. We're reversing it here, right? Because it's not dissociating, it's two things coming together on the left. And so we do 1 over Ka based on our Ka rules. If you're confused on that, go ahead and view the previous video. And then we have, for the second one, it's the same thing. For H0 plus, the Ka is 1, the dissociation. And then for H2O, it's Kw. So Kw is 10 to the negative 14. That's something that you will want to know off the top of your head. Okay. Then for our rules, right, we know that this K, the K that we want I'm gonna do this in a different color. That just so we can distinguish them from each other is going to just be all of these K's multiplied together. KC1 times KC2 times KC3 times KC4. All right, so then we just plug in everything. 1 over 5.8 times 10 to the negative 10 times 1 over 6.6 times 10 to the negative 4 times 1 times 10 to the negative 14th. Okay. I think it's going to end up being like A or B when you plug this all in. Give me 1 sec. Yep. So the answer here ends up being A. 0.027. And then that's it. All right, number 9, it says a saturated aqueous solution of calcium hydroxide has a pH of that. What is the molarity of calcium in such a solution? For this, first let's write out the chemical equation. Oops, there we go. Like that. So you can see that there is, for every calcium hydroxide that dissociates, there's twice as many hydroxides as there is calcium. Now, how we do this is we're going to relate pH that we're given to POH. Why? Because of this reaction. So in this reaction, if you dissolve some calcium hydroxide, assuming that there's no or a negligible amount of OH already in the water from the autoionization of water, then we're going to have twice as many moles of hydroxide as we do calcium in the solution. And if we have twice as many moles of hydroxide, we're going to have twice the molarity of OH minus. And if we have twice the molarity of OH minus, right, if we can figure out what the concentration of OH minus is, then we can figure out the concentration of calcium, right? We get the concentration of OH minus from POH. The P just indicates you're taking a negative log of something. So pH is negative log of H plus, concentration of H plus, POH is negative log of OH minus, pKa is negative log of Ka, so on. So we know we have this equation, pH plus POH is equal to 14. And we get POH is equal to 14 minus pH, so just basic algebra, subtracting pH from both sides. Now, we also know that POH is equal to the negative log of the concentration of hydroxide. Now, no, I'm not plugging in anything right now because I want to avoid any round off mistakes. I'm going to plug in everything at the end. Again, I know people are more comfortable with numbers, but and actually, let's just do the pH. I usually plug in everything at the end to avoid rounding off numbers, but you do want to get comfortable with variables so you don't make any rounding mistakes. So 14 minus 12.25. I think in this case, it'll be more comfortable for people, and it's okay because we actually get a decimal, a finite decimal that's not going to get rounded. So we have POH is equal to 1.75. Now we can plug that into this equation down here. We have 1.75 is equal to negative log of the concentration of hydroxide. And then we solve for the concentration of hydroxide, and we get 10 to the negative 1.75 using logarithmic rules. All right, so then what we can do is not plug this in yet. I'm going to say the concentration of calcium is 1/2 the concentration of OH minus, right? Because there's half as many calcium ions as there is OH minus. Now, again, I'm making the assumption that there's basically no hydroxide in the solution or there's a negligible amount. Now, this is okay to do because the solution is saturated. So that means we have dissolved so much calcium hydroxide that no more will dissolve in the solution. So it's going to be very negligible amounts of OH minus from the autoionization of water compared to what's given by the calcium hydroxide dissolving. All right, and then we have concentration of calcium is 10 to the negative 1.75 over 2. And then we can just plug this in. We get 0.0089 molar. And that's it. Number 10 says if 1 mole of barium hydroxide is added to enough water to make 10 liters of solution, the resulting pH of the solution is what? So we can write out the equation. We're doing basically the same thing for this one, just backwards. So we start with the chemical equation. Now I'm going to assume that this whole thing dissolves because I don't think you've learned KSP yet. So solubility equilibrium. I'm going to assume all of this dissolves. Okay. And then that means we have 2 moles of OH, right? You could write out the whole equation. I mean, you could say I have 1 mole of BaOH2. If you want to do all the math, right? You have 2 moles of OH minus for every 1 mole of BaOH2. You get 2 moles of OH minus, right? All right, so now we can use our molarity. So the molarity of OH minus is going to be 2 moles over 10 liters, which is 0.2 liters, molar. And then we want pH. So again, we're going to go to POH because we can get pH from POH. So POH is negative log of OH minus negative log of 0.2. 0.699. Okay. So that's our POH. And then we're going to plug this into pH plus POH equals 14. pH plus 0. I'm just going to put 0.7 is equal to 14. And we get pH is equal to 13.3. Then the answer is A. So it says, what is the pH of 1.0 times 10 to the negative 9th molar solution of nitric acid? So this one you have to look at the concentration. So typically we ignore the autoionization of water because the autoionization of water is negligible compared to that of the acid we're adding. Now, just so you know, the concentration of H plus is 10 to the negative 7th, or 1 times 10 to the negative 7th, in a neutral solution. So that's a pH of 7. So if you're looking at these two numbers, the concentration, and this is from autoionization of water. So if you're looking at you have to look at the concentration of the nitric acid. It's 10 to the negative 9th. That's 100 times smaller than that from the autoionization of water. So the concentration, or no, not even a concentration, we're gonna say the H plus from HNO3 it's really negligible compared to the H plus from the auto ionization of water. And because of that, we're just saying that the concentration of H plus is pretty much equal to the concentration of H plus from just the auto ionization. So we're not adding the nitric acid. You could, honestly, I mean, you could, and you're going to get the same answer here. And the answer ends up being 7, right? If you really wanted to be super mathy about it, you could say, it's not a bad thing to be very mathy about it, but you could do it like this too. You could say pH is equal to, and then you can add the concentrations. So 10 to the negative 9th plus 10 to the negative 7th. And then this is 6.996, which is 7.0 to 2 digits, right? Where this is from HNO3, this is from H2O. Both are totally acceptable ways to go about it. This is honestly probably a better way to do it, but so you intuitively know that concentration is negligible because you do this a lot, right? With other things, you don't consider the auto ionization of water, like we have not been in the past few problems. All right. Number 12, it says you have 0.272 grams of a monoprotic acid with that molecular weight. It's dissolved in water to produce 25 milliliters of a solution with that pH. Then it says determine the ionization constant, so that's Ka, of the acid. So let's just say the acid is Ha. It's in equilibrium with A minus and H plus. Okay. So if you want to write the Ka of this acid, it's going to be A minus times H plus over the concentration of HA. Right. So I think you've seen this problem quite a bit, and you've probably already seen it on the OLI homework. Then this is about equal to A minus, or whoops, sorry, H plus squared over the initial concentration of HA. The initial concentration, because when we do the ice table, right, you subtract X and so on. But I'll leave that out since I don't think many of you are used to that. The reason I say it's approximately equal to is right because we're not considering the auto ionization of water. So it's pretty much the same, but it's not exact. So if you do this ice table, we want to find Ka. Now, if we're doing an ice table in molarity, I don't have the initial concentration of HA. I am, however, given the grams I put in and the molecular weight and the volume of the solution. I think you see where I'm going here. So the moles of HA, I'm going to do it on the right or left, is 0.272 divided by 189, right? Grams divided by molecular weight. And the molarity of HA is equal to the moles divided by the liters of solution. Right? 25 milliliters is 0.025 liters. Don't mix that up. Then when we plug this in, we get 0.0576. So 0.0576 for the initial concentration, right? You have minus x plus x plus x. Then we have 0.0576 minus x, x, and x. You can plug this in for the Ka, right? This is x squared. And this is 0.0576 minus x. Oh, whoops. Sorry. No, we already have x. We actually figured that out. So for x, well, we know the concentration of H plus is equal to x. We're also given the pH. Well, the pH is equal to the negative log of the concentration of hydrogen, right? So what we can do is go ahead and get the concentration of hydrogen. Move all this. 10 to the negative pH. And then we get that. Now, 10 to the negative 4.93 is not, it's small, but, and it's pretty negligible compared to HA, but I'm not going to drop it just to make sure we don't lose any precision when calculating Ka. So then we go ahead and plug this in. So we have the concentration of hydrogen squared on top. That's going to be 10 to the negative 4.93 squared. The concentration of HA, right? Keep in mind this is equal to X. So is 0.0576 minus 10 to the negative 4.93 because it's minus X. X is the concentration of hydrogen. And we're subtracting it on the bottom. Then we plug it all in. And we get a very small number. 2.340 times 10 to the negative ninth. So the answer is E. That's how you do that, right? Start out with what you need to find. So Ka, write your expression for Ka, and then figure out where you can get those quantities from. All right. 13, it says hypochlorous acid has an ionization constant of that. What is its percent ionization in a 1 molar solution of HOCl? So hypochlorous, I'm just going to write this H plus OCl minus. Now, if you want to find the percent ionization, so what is that? The percent ionization is going to be the concentration of the ion. So in this case, H plus, it could also be OCl minus. Actually more accurate to do OCl minus because H plus is from the ionization of water as well, but we're not going to consider it. And then, oops, over the initial concentration, then times 100%. So you're basically seeing how much dissociated. So if it's 100%, then they would be the same. So it'd be a strong acid. If it's less, which it's going to be, then you get some number that's not 100%. So we need the concentration of H plus. That's what we need, right? We need this thing right here. So we're going to get it from our ice table. We start with 1 molar solution of HOCl, right? Also note this ice table is a molarity. For H plus, we're going to assume we start with 0 and 0. Right, we're not going to consider the autoionization of water. Then we have the change, minus x, plus x, plus x, 1 minus x, x, x. Then we can use Ka. So this is Ka, right? We have Ka is equal to H plus OCl minus over HOCl. Then we can go ahead and plug everything in. 3.2 times 10 to the negative 8th over x times x for 1 minus x. Now we're going to make an approximation here. One sec. On the top, we have x squared. Now the approximation we're going to make is we're going to say that x is so much smaller than 1. So 1 minus x is about equal to 1. That way we don't have to do so much math. Avoid using the quadratic formula. Here you just take the square root on both sides now. And we get x is equal to 1.79 times 10 to the negative 4th. So now we get to go ahead and plug that in, right? X is the concentration of hydrogen, right? From our ice table, just over here. So then let's just plug it in. 1.79 times 10 to the negative 4th over 1 times 100%. And we're basically getting the same thing. So it's going to be about, oops, 0.018%. Did not see that answer. Don't know what was wrong. All right. On to the next. So this one, it's going to be the value of the conjugate base that this Ka correlates to. So for H3PO4, the first hydrogen correlates to K1. The second hydrogen correlates to K2. Oops, that should be 2 minus. And then the third hydrogen correlates to K3. So I said it correlates to the conjugate base of the acid of the second hydrogen, or yeah, wherever the second hydrogen gets removed. So in this case, the second hydrogen comes from H2PO4. And then it's the conjugate base of this one, so HPO4. So if it was K1, let's say, you're looking at Ka1, then it's approximately the value of H2PO4 minus, or Ka3, right? It'd be PO4 3 minus. Quinine is a diprotic base, meaning that it can receive 2 protons. If quinine has a concentration of that, find the pH. Then we're given both its Kb1 and Kb2 values. So the first thing we can do is use Kb1. And we know Kb1 is about equal to the concentration of OH minus over the concentration of the base, which is quinine. And then what we can do is solve for the concentration of OH minus and then find the pH. Now I'll talk about after we find the concentration of OH minus, but we're not going to look at Kb2. So we're going to do this. We're going to say Kb1. Actually, I'm just going to go ahead and algebraically solve here. We get K square root of Kb1 times the concentration of quinine. Quinine is equal to the concentration of OH minus, right? Just algebra, multiply both sides and take the square root. And then we get the concentration of OH minus to be 1 times 10 to the negative 6 times 0.002. Then this gives us 4.47 times 10 to the negative 5th molar. Now, what we do here to greatly simplify this problem is we're going to say that even though quinine is diprotic, Kb2 is very small. So we assume the second protonation of quinine negligibly affects pH to greatly simplify this. Or in other words, we're not using Kb2. So again, we're just assuming that it does happen, but not enough to affect what's happening here. To make this way, way, way more simple. Otherwise, you're going to have to basically do 2 ice tables. If you really want exact answers, right, you would have to do 2 ice tables. Depending on the molarity, you might not be able to make some approximation. You'd have to use the quadratic formula, so on and so forth. And it just takes a while, right? And then you have kind of a two-way ice table because then it's affecting the first protonated quinine, and then it's just kind of it gets complicated, right? Just trying to get an exact answer. So let's not do that. Let's assume that it doesn't really affect the problem. Then we're going to get pH is equal to 14 minus POH. Oops, there we go. Which is 14 minus, or 14 plus, because it's minus the negative log. I'll write it out for those of you. Negative log of the concentration of OH minus. Then we just go ahead and plug in. We get 9.65. And then we're done. Okay. 16 says, which aqueous solution will be acidic? NaF, KNO3, CaCO3, NH4Cl, or E. So you're looking for the one that can give off. So assume all these fully dissolve in water. That's the first one. Actually, you don't even say fully dissolve. No, let's say fully dissolved, just to simplify it. So assume all these ion complexes fully dissolve in water, or just ions. Sorry, ionic compounds. What am I saying? So assume all these ionic compounds fully dissolve in water. Well, if you look at each of these, so NaF, well, with NaF, you have Na, which doesn't do anything in water. You have F minus, which is a weak base. So it's going to end up producing OH minuses. So it can't be A. Really, you're looking for the one that gives off an H plus. For B, the potassium and the nitrate don't do anything in water. NO3 is one of those. It's the conjugate base of HNO3, which is a strong acid. So it's not going to do anything. It's just going to float around in water. Won't produce any OH ions. So it's not B. And then the one, if you look down here, calcium carbonate won't do anything either, but it's going to be D for your answer here. So with D, you have NH4 plus, and NH4 is a weak acid. And it's the only one that gives off an H. So that's why we're picking it. All right, this one says, which solution will have the lowest OH concentration? All right, so which one is essentially the weakest base out of all of these? All right. So all of these, except for NaCl, can act as a base in water. So both of these can act as bases. H2SO4 is a weak acid. And it's because H2SO4 is a strong acid. So you don't really get this equilibrium, even though HSO4 has a minus, and even though it's a conjugate base to an acid, it's a conjugate base to a strong acid. So you're assuming that the equilibrium does not go backwards. Just like with HCl, you assume the equilibrium doesn't go backwards. NaCl doesn't do anything. So HSO4, right? You may think that it could act as a base. It cannot because of the conjugate acid being strong. That one's neutral in solution. So the answer here is D. The one with the least OH concentration is going to be the one that is the least basic. Or the most acidic. And that's it. All right, number 18 says, what is the pH of this? So we're basically going to do what we did with the other problems. We're going to say, so assume we have a Ka. The Ka that we do need for this is 5.8 times 10 to the negative 10th. Should be given, or you can look on the table. And we know Ka is about equal to this. H plus the concentration of the acid. And then, oops, if you were to do, no, we don't need to do a nice table because we're making the assumption here. So then we can just go ahead and solve for H plus. Right, the really appropriate way to do this would be do a nice table, make the assumption, but I think we've done it enough times where you can just use this. Remember, this is an approximation. And we also don't have room to do a nice table. All right, so we get h plus from this is equal to that square root of Ka times NH4 plus by algebra. 0.035. So when you plug it in, you get 2.03. Oops, no, you don't. I didn't take the square root. We get 1.42 times 10 to the negative fifth molar. Then we can plug this into the pH formula. (1.42 times 10 to the negative fifth). And then, oops, we get 4.85. And that's it. This is a common formula you can use for your weak acid. Again, it comes from the ice table and making the assumption that the pH is negligibly affected. Or sorry, not the pH, that the concentration, initial concentration of the acid is negligibly affected by dissociation. Okay, number 19 says fill in the table identifying whether the solution of each of the following is an acid, basic, or neutral. So if you're looking at the table, oops, whoa. So the way you do this is you have to determine whether you have a conjugate base of an acid or whether you have something that is an acid. Where on this table, and it seems like for most of your class, you're not really assuming that you have like a conjugate conjugate base from the first ion. So in the cases of 4 and 5, this is important. You're going to assume that calcium cannot act as something that's insoluble, something that'll pull out OHs from the water from autoionization. Because if that's true, then you'll get a different answer. You're gonna end up getting acidic things. So let's assume that you either are only looking for conjugate bases of weak acids or weak acids, really, in your ions. So if you're looking at NaNO2, Na plus is not a weak acid. NO2 minus, though, is the conjugate base of a weak acid. And because of that, this ends up being a basic solution, right? Why? Because if you write out the equation, we have these two. So we have both of these. If you add NO2 to your water, oops, that should be NO2 minus. If you add NO2 minus to your water or a solution, it's going to combine with H pluses to form HNO2, right? Because there's an equilibrium. Well, you're removing H pluses. If you're removing H pluses from your solution, by Le Chatelier's principle, in the second one, where you have the autoionization of water, you're going to push this reaction to the left, and you're going to produce more OH minuses. So now you no longer have the same amount of H pluses and OH minuses. You have more OH minuses. So the solution is therefore basic, right? So you can explain this with Le Chatelier's principle. You can explain it with pH too, right? You can also say, well, if I'm decreasing the number of hydrogens, as the number of hydrogens goes down, then pH also goes up. right? Because more hydrogens, pH goes down, less hydrogens, pH goes up. So 2 ways you can explain it. For KCl, it's neutral. It's just potassium, which is not a weak acid, and chlorine, which is not a conjugate base. It's a conjugate base of a strong acid, but it's not the conjugate base of a weak acid. So basically, again, there's no equilibrium. That's what we're looking for here. And then NH4 is a weak acid. So this is acidic. For calcium and chlorine, we're going to assume that calcium does not pull hydroxide from water. Otherwise, it would change this. For chlorine, we already said it. It's the conjugate base of a strong acid, so it doesn't reform H plus or HCl, sorry. All right. It's not reversible or negligibly reversible. And then we have, it's not technically true, but it's true enough for all of these. And then we have CaNO2, 2. So this one, we, for the same reason as the first one. NO2 is the conjugate base of a weak acid. 20, it says, which indication of relative acid strengths is incorrect? HCl is bigger than HF. So that's true because HCl is a strong acid, HF is a weak acid. The reason why is HF is more electronegative. It wants to hold on to that proton a lot more than Cl does. So A is correct. Next, we have chlorous acid versus hypochlorous acid. So for this one is correct. As you go up in the series for the ClO series, it becomes stronger and stronger acid. So hypochlorous acid it's a strong acid, but it's weaker than chlorous acid, which is weaker than chloric acid, which is weaker than HClO4, perchlorous acid. Then we have C, H2SO4 is stronger than H2SO3. That's true. H2SO3 is a weak acid. H2SO4 is a strong acid. Then we have H2SO3 is stronger than HNO3. That one is incorrect. HNO3 is a strong acid. This one is a weak acid. All right, last one, 21. It says, oh, we can even double check the last one if you're curious. We have CH2, Cl, CO2H, and then CH3, CO2H. So this one's actually true. Not for any reasons that would be obvious to you. This has to do with inductive effect. So for those of you who take organic chemistry, you'll learn this. But if you're not sure about an answer, don't choose it unless you really don't know. Then I guess you should guess. But if you're not sure about an answer, don't choose it. So in this case, the only one that we know for sure, based off of what you know, is going to be D. 21, it says indicate the first and second most acidic proton in the lactic acid shown below. Also some organic chemistry here. So things that are next to these C double bond O groups are most acidic. So that one, we call them carboxylic acids. So I should say things next to the C double bond O and are on an oxygen. So the C double bond OH, this is a COOH group. Excuse me. And then we have this OH down here, which is the second most acidic because it's on an oxygen. So H's on oxygens are more acidic. Again, this is not obvious for any reasons that I think you've learned so far. Really, the video is done. So if you would like to, you got this far, thanks for watching. Hope that helps. I'll give it an explanation now on why this is for those of you that are curious. So for the first proton, actually, let's talk about for why oxygens are more acidic, the ones that have H's than carbons. The reason why is that oxygen can stabilize the negative charge better than carbon can. So oxygen is more electronegative than carbon. So if you lose the H and you have an O minus, it can hold on to that charge better, right? It's just better at managing those extra electrons and being more stable than carbon can. And again, that has to do with electronegativity. For the group on the right, the COOH group, or the carboxylic acid, it's extremely not clear for those of you who are watching this, but it's going to be due to resonance. So if you take OChem, you'll learn about it. But basically what the double bond allows is a resonance structure where the electrons can kind of move freely between both oxygens. It's not technically correct. It's more of a hybrid, kind of in between. They're shared equally, but they can be distributed quote unquote evenly between the two oxygens because of the double bond. Again, nothing that's obvious from what you've learned, but that's it. So I hope this video helps. We'll see you again in the next video, and best of luck on your midterm.